like to introduce now Dr. Steve Montzka. He's a research chemist with NOAA ESRL. He's in the GMD, Global Monitoring Division. He got his PhD at CU in 1988, took an NRC postdoc with Fred in the aeronomy laboratory. Is that right? And he is now leading the study of CFC alternatives to be used in industrial processes and studying their persistence in the atmosphere. He's been awarded the Department of Commerce Silver Medal for his work. Steve, would you come on up?
Thanks, Bill. So it's great to be here today. I can't say that it's great to be back to Boulder because I never left. And so that's maybe why some of why I'm here today, to talk a little bit about the relationship between CIRES and NOAA viewed from both sides, both as a graduate student and then across the street from the NOAA side. And I'm happy that more recently the connection's been remade through me being a CIRES fellow. That's been great fun so far. So when I think about the CIRES, or the CIRES influence on my career, I think first about why, or the decision I made to even come to Boulder. 30-some years ago. In 1992, I wrote this in a family genealogy. Okay, so I was an idealistic young man, wanting to save the world, interested in environmental studies, and that probably could have been said for just about everybody who was graduating from school about that time. But I took a little different path than most of the folks and decided to major in chemistry. And that enabled me to become proficient measuring chemical compounds in the air and water. And so that's kind of the path I took. And so when I was looking at graduate schools, CU and CIRES were the perfect fit. There was a tremendously strong environmental science component to the research ongoing here. And issues that I was interested in and that were at the forefront of the work being done within CIRES, within the chemistry department at CU. And this meaningful and interesting work is really was a major reason I came to Boulder in the first place. And I can imagine that's true for many of the students that end up here working at CIRES. Okay, so Bob and Rosella, thanks for sharing this picture. So this is the CIRES group around about 1983. I can tell because Jennifer Tavernier was in the same year that I came to school, graduate school here. But I'm not in this picture, and I'm not quite the same IT expert that Dave is. But I joined. Recently minted graduate, joining the group here in Boulder, and starting my career as a graduate student. And certainly, as a graduate student, many good times, gained valuable research in how to conduct, valuable experience in how to conduct research, chromatography, and atmospheric measurements of hydrocarbons. But I must say the most significant and wonderful aspect of this graduate career will have to do with this nice lady right here sitting in the back, my wife of the past 25 years. So I wasn't in the picture, but I do have proof that I actually was here. This is Valentine's Day, 1984, my first CIRES seminar, literature discussion of the Denver brown cloud. Once upon a time, Denver was a mecca for people with respiratory ailments. They traveled from afar to take in the pristine mountain air. Today, however, a quick glance in the direction of Denver would lead to one to believe otherwise. So that was great fun. I still remember some of those slides I showed in that talk, but I'm going to save you from that today. I think an equally important part of my CU CIRES graduate career was being exposed to the broader atmospheric science community in Boulder. It seemed that Boulder was the center of the universe for scientists tackling significant atmospheric environmental problems today related to ozone depletion, tropospheric ozone formation, acid rain, and oxidant formation. As a graduate student, this drew, this drew a lot of people to CU. It drew a lot of people to NOAA, and the experts, many of the experts were at NOAA, and I got to participate or be part of those seminars, and really that it was very exciting to see and go to seminars where people who had just come back from Antarctica. This was just as the ozone hole is being discovered. Just come back from missions in Antarctica and sharing with us their findings and learning about the real causes behind the ozone hole at that time. Being here at CIRES allowed that to happen. It was very exciting. It also allowed some investigations of, this is a question here, but actually it was quoted as a statement by some very high political person that trees cause more pollution than automobiles. So we were trying to assess, this issue was also a big question and the research ongoing in Boulder. So after I graduated, I took an NRC postdoc position at NOAA with Fred Fazenfeld and Paul Golden. We were measuring oxidation products of emissions from trees and aldehydes and ketones and identifying new chemical emissions from plants, the methylbutanol. And I'd also like to mention a number of people involved in my mentoring there during my postdoc. And I would also like to mention Michael Trainer, who was a CIRES employee then, who was instrumental in, even though he has nothing to do with instrumentation, he's instrumental in helping me understand what the measurements that we were making at NOAA meant. And so he played a large part in my career there. So I liked how NOAA worked, and so after my postdoc, I went to the Elkins group at NOAA, the Climate Monitoring Diagnostic Lab. This is a picture from the early 90s. I joined that group with the ostensible job, the mission of monitoring ozone-depleting gases in the atmosphere. I put monitoring in quotes because I think we do a whole lot more than that. And I hope to show you that briefly. But the one point I want to make about this in relation to CIRES and NOAA is that then and now, this group was comprised of more than half of the folks in this group are CIRES employees. CIRES employees are integral to what we're able to do, both the main mission, but also improving our understanding about certain issues that help us better fulfill our main mission. So what do we do exactly there? Well, there's a suite of sites around the world where we have some instrumentation. It's nice to see Jeff Dutton here. Maintains the instruments at those sites around the world. And we also get flasks from all the non-red locations here sent to Boulder. And so the job description was take samples from these locations, measure the replacements for ozone-depleting substances starting today and not ending. Potentially not ending. That may change, I suppose. But, and so I was a little bit hesitant in the beginning to try to, to imagine that, could I keep interested in this job? And I think when I started thinking about monitoring and what it involves, it's kind of a process that has a high activation energy. It takes a lot of effort, time, dedication initially. You don't get much back, maybe. But once you're past that point, you get an awful lot back, and it's very rewarding. And I think we're at that point now. So we make measurements of these gases, and we're now at the point where we're benefiting from the spoils of atmospheric monitoring. I first want to discuss the ozone hole and ozone-depleting substances. I mentioned that I came to this position at NOAA in the mid-1980s, early 1990s. My main goal was to measure the replacements, and most of the work that had been ongoing there was measuring the main gases involved in ozone depletion. And so soon after I was there, we were able to put together the picture that less than 10 years after the Montreal Protocol on substances that deplete the ozone layer was ratified, ozone-depleting halogen concentrations started to decrease in the atmosphere. So in other words, the Montreal Protocol was working. We were able to see, here's the measurements that we're making and the points here and the progression of the results to the present time of how ozone-depleting halogen has responded to the Montreal Protocol, how it's changed over time. And it's decreased rather substantially. And I show the 1980 level in here because this is This is the point at which ozone depletion was particularly noticeable. It was it started, people when they say, when was ozone depletion becoming severe? And it was about 1980. So when ozone depleting halogen concentrations decline back to this level, we would expect that the hole may be mostly healed. So this was very nice to be able to see happen in the atmosphere and to document it and to communicate it to the world. And when I take off my scientific hat for a little bit and think about what this really means, and one can say different things about the design and the approach of the Montreal Protocol, specific things that allowed it to be successful. For example, that it was kind of a small first step, and that allowed for revisiting of the controls on different gases with regular input from scientists. And the fact that it allowed or provided for a 10-year grace period, for example, for developing countries. All these things made it successful. And I think have implications for policies potentially to limit the influence of greenhouse gases on climate change. But in the end, this is policy-relevant science from the NOAA CIRES collaboration, bringing both groups together to tell a story that has significance, I think. So that was just an accounting story, mostly. But our goal at NOAA is not only monitoring, but also improving understanding and improving our predictive capabilities. And CIRES provides NOAA added flexibility and the capability to address fundamental questions of interest that perhaps aren't our main mission, but are very closely associated with it. And the outcome, of course, is improved science and more accurate information to policymakers. And so there's a number of things that I'll just briefly go through here, if I can, related to certain issues that demonstrate that. In the late 1980s, early 1990s, folks were trying to consider whether or not methyl bromide was worthwhile controlling in the Montreal Protocol. The budget of methyl bromide, the fluxes, were poorly understood. Were anthropogenic contributions significant enough to warrant its control so that we would see some benefit if controls were put into place? And so Jim Butler led a study along with some CIRES postdocs to look at methyl bromide fluxes from the ocean. And the results that they supplied, and of course other studies that were done related to methyl bromide, showed that humans probably contribute maybe 30% of the methyl bromide in the atmosphere. So it may indeed be that we would benefit quite substantially if methyl bromide were controlled. And lo and behold, we've been able to monitor in the atmosphere methyl bromide concentrations. That's what we do. And we see this decline after production decrease. This is northern hemisphere mean mixing ratio, southern hemisphere mean mixing ratio, and the average of the two, a decrease over time. So a notable change in the atmosphere and the contribution of this gas to atmospheric halogen, ozone depleting halogen. So a nice combination of work done by CIRES and NOAA to investigate a chemical further and supply some added information about whether or not controls would have a benefit. There was also questions about what the concentrations of ozone-depleting substances before they were produced industrially were in the late 1980s and 1990s. For methyl bromide, there was a strong natural component. For CFCs and other things, there was the potential that some of these chemicals were produced as a result of volcanic eruptions, for example. And so we were able to go to different locations, Antarctica and over Greenland, to dig down into the snow and extract air that had been buried. And this allowed us to reconstruct atmospheric changes over the past 100 years so that we could see what the concentrations of these gases were actually before they were produced industrially. And of course, what we found was what we expected in this case, and that was that the concentrations of CFCs and HCFCs and most chlorinated solvents were essentially zero in the oldest air. More recently, we've looked at the oxidizing capacity of the atmosphere and how it could change over time. And this is expressed as the atmospheric hydroxyl radicals, central to tropospheric chemistry. And there's many questions about, it's very difficult to measure, especially on broad scales. And so there's questions about what its mean concentration is and how it varies. Is the ability of the atmosphere on a global scale actually quite sensitive? Is the ability of the atmosphere to cleanse itself of pollutants quite sensitive from one year to the next? Or is it robust? And Montreal Protocol actually gave us a wonderful opportunity to study this, where methylchloroform, ozone-depleting substance, whose production was limited and emissions declined dramatically afterwards. And what did we see in the atmosphere as a response? An exponential decay in its mixing ratio. The concentration of gas in the global atmosphere is determined by sources and sinks, or loss processes. You take away those sources, and the observations provide you precise information about those loss processes and how they change over time. And this record enabled us to do that, to show that really it looks like during this period anyway, the atmosphere's oxidizing capacity has been fairly robust and constant. And finally, more recently, we've been looking at carbonyl sulfide to help quantify rates of photosynthesis. Carbonyl sulfide's very similar chemically to carbon dioxide, and this link is seen in the atmospheric changes seasonally. And even we've had another connection with CIRES here, in that Dan Yakir is a CIRES visiting fellow, just ending his stay here in Boulder, and that's been nice to have him here to provide some additional insight into the measurements that we're making at NOAA. And I think any talk about what I've spent my time on over the years would have to do with what is my second job at times, and that is participating in communicating science results to a wider audience, and that is through scientific assessments. Because our goal in doing this is to supply policy-relevant but policy-neutral information. I've heard this probably 1,000 times from retired Mr. Dan Albritton. And Robbie certainly has continued that mantra. So in summary, as a student, it's clear that CU enhanced my education tremendously and helped me decide to come here to Boulder. And now that I'm at NOAA, I look back and I see, or I look around even in the building that I'm in, and see that CIRES employees are integral to the research that goes on at NOAA GMD. They provide a means to explore key science questions, and without the capabilities that CIRES affords, we'd be severely hampered over there. There's no doubt about it. And personally, the NOAA-CIRES relationship greatly enhances my professional life at NOAA, given the things that we can do in addition to just accounting. And so many thanks to the number of collaborators and colleagues, friends, and family for helping me along over these many years. It's good to be back here. Thanks.